Hello everyone and welcome to this third presentation about the catalytic hydrogenation of alkenes. This video is about the reduction of alkenes without hydrogen. I'll show you a few examples of transfer hydrogenations, that is, hydrogenations with typical heterogeneous or homogeneous catalysts and some reagent that can generate hydrogen in the reaction mixture. But there are also reagents that can convert alkenes into alkanes without any transition metal catalyst, and these can be valuable alternatives if a given starting alkene is not compatible with catalytic hydrogenation. Transfer hydrogenations are particularly useful if the amount of hydrogen must be dosed precisely, or if no hydrogen or hydrogenation equipment is available. I'll show you some typical hydrogen sources in a minute. Olefins can also be reduced by treatment with a diimide, which is a highly reactive intermediate formed upon oxidation of hydrazine. Electron-deficient alkenes, such as enones or acrylonitriles, can sometimes be reduced by treatment with alkali metals, magnesium or zinc. There are also procedures for the one-pot hydrogenation of alkenes by hydroboration and protonolysis of the intermediate boranes. A similar strategy, namely hydrosilylation followed by protonolysis, can also be realized with silanes. Unlike boranes, however, silanes are also good hydride donors, and alkenes that readily form stabilized carbocations upon treatment with acids can be reduced by treatment with triethylsilane under acidic conditions. Electron-deficient alkenes, or alkenes close to a hydroxyl or amino group, can sometimes be hydrogenated by treatment with lithium aluminum hydride. Unfortunately, this reagent is not very selective, but such hydrogenations can be a valuable alternative in special situations. Here's a list with some typical reagents suitable for transfer hydrogenations. Most of the catalysts presented in parts 1 and 2 of this playlist can be combined with these reagents to bring about the hydrogenation of alkenes without the need of any gaseous hydrogen or autoclave. If vapors of these reagents come into contact with a dry heterogeneous catalyst, the catalyst will become hot and may catch fire spontaneously in the presence of oxygen. If a given alkene contains any of these functional groups, treatment with a hydrogenation catalyst in the absence of hydrogen can cause dihydrogenation of this functional group and simultaneous hydrogenation of the alkene. Diimide has often been used to hydrogenate olefins that could not be hydrogenated with a transition metal catalyst. The most common way to generate diimide is by careful oxidation of hydrazine with oxygen or hydrogen peroxide. Stirring a solution of the olefin, hydrazine, and catalytic copper-2 salts under a slow stream of air is a practical way to perform this reduction. It should be kept in mind that hydrazine may ignite spontaneously when mixed with concentrated hydrogen peroxide. Another common way to generate diimide is by acidification of a salt of azo-dicarboxylic acid. Further methods include heating sulfonyl hydroxides or mixtures of hydroxylamine and ethyl acetate. Because of the high reactivity of diimide, an excess of the reagent is usually required. Let's now have a look at some specific examples. I've chosen mostly cases with some selectivity issue. Here, a substituted styrene was reduced stereoselectively to the trans product by treatment with lithium aluminum hydride. The cis diastereomer could be prepared by catalytic hydrogenation with palladium on charcoal. No cleavage of the benzylic amine or the carbon-fluorine bond occurred. Still more reactive toward hydride or single electron donors than styrenes are alkenes with an electron withdrawing group, as in this example. Such olefins can be reduced with sodium borohydride or with metals, such as magnesium in this instance. This is a rare example of enantioselective hydrogenation of an enal with diimide. With the aid of 10% of an enantiomerically pure pyrrolidine and only 1.2 equivalents of potassium azo-dicarboxylate as diimide source, an excellent yield of saturated aldehyde was obtained, without any reduction of the nitro group. This is an example of transfer hydrogenation with a soluble rhodium catalyst. As hydrogen source, triethylammonium formate was used, and again nitro groups remained unchanged. alkenes containing reactive alkyl halides can be difficult to hydrogenate without carbon-halogen bond cleavage. In this example, an alkylating anti-cancer drug was prepared by reduction of an enamide with an excess of zinc in acetic acid. Enones and other electron-deficient alkenes can often also be reduced with this method. Here, an electron-deficient alkene was reduced with sodium borohydride. Because of the benzyl ester, the cyclopropane rings, and the vinylic chloride, catalytic hydrogenation might have been difficult. A fair yield resulted though with borohydride, without extensive cleavage of the carbon-chlorine bond. In this example, a vinyl iodide was hydrogenated with diamide generated by oxidation of hydrazine with potassium hexacyanoferrate. Despite the excess of diamide, only one of the two double bonds was reduced. This is a further example of the hydrogenation of a vinyl iodide. Here, a rather complex mixture of reducing and oxidizing reagents was used to bring about the reaction. Unfortunately, also one equivalent of cobalt acetoacetate was required. Anyway, although such a procedure can't be scaled up, its mechanism may point toward new hydrogenation strategies. A number of additions to alkenes have recently been published that are based on the mechanism sketched here. Instead of cobalt, also manganese complexes can be used as catalyst. It is assumed that the combination of peroxide and silane converts the cobalt-2 complex into a cobalt hydride. This intermediate can add to unactivated alkenes, whereby a thermally labile cobalt-alkyl complex is formed. Homolytic cleavage of the cobalt-carbon bond then yields an alkyl radical and the starting cobalt-2 complex. The alkyl radical may now react with any additional reagent present in the reaction mixture, or with the starting alkene if the concentration is too high. In the previous example, a large excess of silane and cyclohexadiene led to a reduction of the radical and formation of a saturated alkane. I'll show you a further example of this strategy in a minute. I'm not a fan of mixing oxidizing and reducing reagents with transition metal catalysts, because such mixtures tend to decompose violently. In this case, though, it seems that no direct reaction of the peroxide with the silane occurs. Here, an enone containing a highly reactive allyl bromide was reduced enantioselectively with a silane. As catalyst, a chiral 2-pyridine carboxamide was used, which was assumed to react with the chlorosilane to yield a more reactive, enantiomerically pure silane. In this example, a brominated push-pull enone was reduced with triethylsilane and catalytic amounts of a Lewis acid. Again, no cleavage of the carbon-bromine bond occurred. The electron-deficient double bond of dienes, such as carvone, can often be reduced selectively by hydride donors or metals. Zinc is often used under acidic conditions, for instance in acetic acid, but alkaline conditions also seem to work, as this example shows. Pinacol coupling was one potential side reaction, but did not occur here. Alpha-beta unsaturated carboxylic acids can also be reduced with metals. In this example, sodium in liquid ammonia was used, thus the conditions of the Birch reduction. Neither the carboxylate nor the unconjugated double bond were reduced. This is an example of the selective reduction of a styrene, again under the conditions of the Birch reduction. Here, the conjugated non-aromatic double bond was reduced faster than the arene, but a larger excess of sodium would have converted the arene into a cyclohexadiene. Also, diamide can sometimes bring about the selective monoreduction of dienes. In this example, an allyl alcohol was selectively reduced by diamide generated from hydrazine and oxygen. As catalyst, no copper salts, but 10% of guanidinium nitrate was used. Here, a starting triene had to be reduced selectively. Again, this could be achieved with diamide, generated by acidification of potassium azodeicarboxylate. A further possibility to generate diamide is by heating sulfonyl hydroxides with a weak base, as in this example. Here, again, the sterically more accessible double bond was hydrogenated first and with high selectivity. Unfortunately, aldehydes and ketones will quickly form hydrozones upon treatment with hydrazine or sulfonyl hydroxides. If a given alkene contains these functional groups, diamide would have to be generated from an azo dicarboxylate instead. The CC double bond of allyl alcohols, amines, enones, and alpha-beta unsaturated carboxylic acids can sometimes be reduced by treatment with lithium aluminum hydride, as in this example. Unfortunately, this reagent is a powerful hydride donor and will reduce a large number of other functional groups too. Here, despite the large excess of lithium aluminum hydride, though, the vinyl iodide and allylic ether remained unchanged. Cobalt-based catalysts have occasionally been used for catalytic hydrogenations. In this example, a mentadiene was subjected to a transfer hydrogenation with copper and cobalt as catalysts and sodium borohydride as reducing agent. Mostly the sterically more accessible disubstituted double bond was reduced. Alkynes are hydrogenated at about the same rate as simple alkenes. Because the sp hybridized carbon atoms have more S character and are therefore more electrophilic, alkynes can sometimes be reduced to olefins by metals such as zinc or sodium. In this example, however, it was possible to reduce a highly electron-deficient alkene by treatment with zinc and acetic acid without extensive hydrogenation of the alkenyl group. In this example, an acrylate underwent copper-catalyzed hydrogenation with sodium borohydride, again without any reduction of an internal unconjugated alkyne. Also, dithionite may be used to selectively reduce electron-deficient alkenes in the presence of alkynes, as shown here. Despite the excess of dithionite, no cleavage of the carbon-bromine bond or reduction of the keto group occurred. Here, an allylic epoxide containing a secondary alkyl bromide and tertiary alcohols and ethers had to be hydrogenated selectively. This could be achieved in good yield by treatment with an excess of diamide generated by oxidation of hydrazine. As already mentioned, hydrazine will ignite spontaneously when mixed with concentrated hydrogen peroxide, and the peroxide must therefore be added slowly to the reaction mixture to prevent excessive heating. In this example, similar to the previous one, diamide was generated by slowly adding a mixture of hydrazine and triethylamine to a mixture of the alkene and nitrobenzene sulfonyl chloride. This order of addition was necessary to prevent nucleophilic cleavage of the benzoic acid ester by hydrazine. Despite the excess of hydrazine, the hydrogenated ester was obtained in good yield. Even alkenes containing acido groups can be hydrogenated selectively with diamide. Here, this feat was accomplished with diamide formed by oxidation of only 2 equivalents of hydrazine with oxygen. Olefins containing free thiol groups cannot usually be hydrogenated with noble metal catalysts. In this example, an unsaturated thiol was reduced by phenylsilane using the radical strategy discussed above. Instead of cobalt, in this instance a manganese complex was the catalyst. Unfortunately, the thiol was oxidized to disulfide, but thiols can be regenerated from disulfides with a large number of reducing agents. Also, hydroperoxides are readily reduced under the standard conditions of catalytic hydrogenation. In this example, a styrene could be hydrogenated without peroxide reduction with diamide generated from hydrazinium carbazate and hydrogen peroxide. In this example, the selective reduction of an electron-deficient alkene in the presence of a peroxide proceeded a bit faster than in the previous example. Again, diamide was used as reducing agent. Oximes are usually reduced to secondary amines or hydroxylamines upon catalytic hydrogenation or treatment with boranes. In the presence of a chiral rhodium catalyst, however, allyl oximes can be hydrogenated enantioselectively at the CC double bond. As reducing agent, catechol borane was used, and even tetra-substituted olefins underwent this reaction. Let's now check a few potential side reactions. Although I have shown you examples of selective hydrogenations, many of these had to be carefully optimized to achieve these selectivities. You can find examples of the reduction of other functional groups in part 1 and 2 of this playlist. 1,3-dienes and styrenes are often more reactive than simple unconjugated alkenes. With highly selective reducing agents, it is even possible to perform clear 1,4 hydrogenations of 1,3-dienes, as shown here. When reducing enones or alpha-beta unsaturated aldehydes with metals, one potential side reaction is pinacol coupling or other radical dimerizations. Such reactions may be suppressed by keeping the concentration of starting material low. On this and the next slide there's a selection of some more, mostly recent examples. You can also find this reference list in the description of this video. In my channel you can also find a playlist with 2 videos about the catalytic hydrogenation of arenes to cyclohexanes. These work best with rhodium or ruthenium catalysts and often require higher reaction temperatures than the hydrogenation of alkenes. Anyway, procedures exist for the hydrogenation of even highly functionalized, structurally complex arenes under mild conditions.